And waves basically are where you have these pulses of energy that comes through, okay? And and that pulse of energy is actually going to travel through a medium. That means a material in which it's going to vibrate and pass through. A lot of times when you see a wave, you'll see it move up and down like this. And we'll talk about the different kinds of waves and how they move and so forth. But another wave that's real common that people think about is actually an ocean wave. Okay? Now, mediums, as I said before, these are materials. This is stuff in which that wave can actually, or that energy can actually travel through. And the different types of mediums that are out there are liquids and gases, but the solid is the best for actual sound waves. Light, as we know, travels around us, but light does better in none of these mediums. In fact, of the three right here, probably air or gas is better for light because it doesn't slow it down, okay? But sound needs something to vibrate to move through, okay? Now, what moves in a wave? It's actually energy. So when you see this one, an object will vibrate back and forth. And so that movement along is actually energy. This object will bob up and down, as you can see, but it is energy that is actually moving from left to right, or actually from right to left in this diagram. But this object is just bobbing up and down on there. Now, there are different kinds of waves that we're going to talk about. The first one is a mechanical wave, and this is where it's a disturbance that we see, the vibration there, a pattern there that we see. And sound waves are actually the best example of mechanical waves. You're actually seeing it move. So think of mechanical as movement. And the other one is the surface waves, and these are items that move at the surface of the earth. So an example of a surface wave would be ocean waves or water or air. It's right at the surface. Earthquakes, when they're pulsing through the earth, would be mechanical, but when it reaches the top layer of the earth there, it is actually then a surface wave. Another type is looking at light or electromagnetic waves. When you get energy that's pulsed out there in space from the sun, it moves in various different forms, and these are actually called electromagnetic waves. And these are waves that that actually can travel, and they change your electrical fields. They can change your magnetic fields. Examples of electromagnetic waves would be X-rays, like when you go to the doctor's office, the X-rays or radio waves, or even gamma rays for radiation. Now, let's look at more specifically those mechanical, the movement waves, okay? The mechanical wave, the first type is called a transverse wave. Now, a transverse wave, you'll see right here, it vibrates at right angles or up and down motion like this. Like a true ocean wave will look like this. And the different parts, and we'll talk about the different parts, you'll see you have the crest, which is the top of the wave. And let me get a pen on to actually circle that one. So that top portion right at the top is the crest. And the bottom of the wave down here is called a trough. And how I remember the trough is when you're feeding animals, a trough is actually like a bowl-shaped container where the feed will go in and an animal will eat out of, you know. Another one's wavelength, and wavelength means to go from crest to crest, or you could go from trough to trough. That's a wavelength. But an easier way to count a wavelength is to count a top portion to a bottom portion, a top to bottom. Think about when you're getting dressed. You put your top on, put your pants on, you know, that's a complete outfit. Now, amplitude, taking this resting position here, amplitude is the height of the wave, okay? And it also measures how much energy. And we're going to look at these a little more specific. Another one, as I said, here we have the crest, which is at the top. It's the top of the wave. The trough is the lowest point or the bottom of the wave. Okay? And then another type of mechanical wave is called a longitudinal wave, or it's also called a compression wave. Okay? And let me get my pen going on this one. Now, here you can see where they're compressed together and they're tight together. And then the area where it's loose and kind of out there is called rarefaction. And those are the loose parts of it. Okay, they move back and forth, so it's sort of like an echo. Sound travels, bounces back. That would be an example of a longitudinal wave. They actually move parallel. So in this diagram here, you could see it vibrating when it first came on. Examples of longitudinal waves are sound waves. And let me go back here. The example of a transverse wave is the light waves. So light waves move up and down. The longitudinal waves are sound waves, and they vibrate, as you can see in this diagram right here. All right, now the parts again, the compression are tight together. The rarefaction right here is where they're spread out. Okay, so these are the parts of the longitudinal wave. Okay, now let's look at wavelength. Wavelength again is going from crest to crest, or if I were to draw a line, and let me get my pen on here. If I were to draw a resting position line, let's say this is where I'm splitting the wave in half. This crest up here, or this top part of the wave, match with the trough down here, the trough. Those two parts right there will count as one wave, okay? And that's how you can see wavelength. So right here, a crest, a complete crest to a complete trough will match as one wave or crest to crest, okay? Now in longitudinals, this one right here, a compression wave, what you're measuring is a compression to compression. Just measure that distance there, and that gives you the wavelength. Okay? Now, amplitude, as I said, is the height of the wave. So from the resting position, I'm going to come all the way up, and this height of the wave is the amplitude. Okay? So on the transverse wave, this one right here, you're measuring from the resting position all the way up. So that's the height. The taller the wave, the more energy it's needed for that. Okay, if it's a short wave, it's a very soft sound. If it's a very tall wave, it's a very loud sound. That means a lot of energy is needed on there. Okay? And again, here we have right here the wave diagram. And let me go through these and actually label those. So the crest would be up here. And we'll label that part A. Okay. The trough is down here, this point. And we'll label that one B. Okay. The wavelength, again. Now I'm going to color this in. Wavelength, for me, the easiest way to measure that is one complete crest to one complete trough. Okay. So on there, if I were to measure how many wavelengths there are, there's one top and bottom, another top and bottom, and another top and bottom. So the wavelength is 3 on that one. So you measure a top to a bottom, top to bottom, top to bottom. Okay, now your amplitude is your height, and that would be, coming out, that would be D. Okay, and amplitude and wave height would also be the same thing. These two would be the same. And then your resting position would be this line right here that I'm coloring in red. This separates the crest, the top part of the wave, from the trough, the bottom part of the wave. Okay? Now, a longitudinal wave, again, if I were to draw that and let me see if I can get my pen on here. Let me go back. Get the pen on. And then I've got waves here. Then they kind of go out. And then I'm going to bring them in close. And then bring them out again. And then kind of bring them in tight again. So I'm looking at this one. The compression would be A here. The rarefaction would be this portion in here. And a wavelength would be from a compression to a compression. So that would be the wavelength. Okay? Now, frequency of a wavelength, again, you're measuring a top portion of the wave to the bottom portion. So when I count this, remember, a top to a bottom is 1. 1, and top to bottom is 2. So the frequency of this particular wave, if I were to count this bottom, would be 2 hertz. And the unit for frequency, so it would be 2 hertz. Now, let's say it stops right here, and we don't see that. So it would be 1.5 hertz. Okay? 1.5 hertz. So if you got a part of a wave, it could be that as well. Now, let's practice right here. Remember, count your top to bottom, and that's 1. And remember, it's measured in hertz. So let's look at this one. 1, 2, 3, 4. So the frequency would be 4 hertz, and it's going to be Hz. Okay, now this one right here. Again, we're going to practice this one. Remember, top to bottom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this one would be 10 hertz. So let's say this bottom right here was not even there. If this bottom was not even there, then when I count, go all the way through 9, and then I got a half right here. It's half of that wave, so it would be 9.5. Okay? Now, another thing, let's look at frequency and energy relationships. As the frequency increases, so does the energy. Okay? So if I am increasing the number of waves, then I'm making more waves. I'm actually applying more energy to get more waves to move. Sort of like if I take a slinky or I take a rope and I fling it up and down, then it's going to move very fast, and I have to put a lot of energy in there to get that wave to move up and down. The same with, let's look at our frequency and then also wavelength. Okay, and I'm going to draw this out on here. Here I have, let's do one wave right here where I see this one right here. And then I'm going to compare it to this wave right here. Okay, now it says an increase in frequency means a decrease in the wavelength. So what that means is when I look at my wavelength going from crest to crest.
It's 4 o'clock.
This one right here going from crest to crest and then crest to crest. My wavelength right here is very short. So when I see lots of waves, the distance from crest to crest will decrease. That means the wavelength's going to decrease. But when I see few waves right here, the distance from crest to crest is going to increase. Okay, so they're actually opposite. And also let's look at this one, wavelength and energy. Again, increase in the wavelength will decrease the energy. And amplitude, as the energy of a wave increases, your height or the amplitude increases as well. Just remember, amplitude is the height. And I'm going to try to write the word height here. So how tall your wave is determines, how tall it is determines how much energy is in there. Okay? Now, there is a period. Period is the amount of time it takes for one wavelength to pass a given point. And that relationship means as the frequency of a wave increases, your period decreases. Okay? So let's move on to the next. Let's look at our wave speed formula. Again, here's our nice little triangle that we have here. So what we have right here is that the wavelength, the speed of a wave on this one, which is the velocity or speed of a wave, V of W, speed of a wave, is equal to the frequency, how many waves you see, and then the distance, how long it is to go from crest to crest or trough to trough, that wavelength. Okay, so here's some problems that we have, some example problems. So a wave has a wavelength of 4 meters and a frequency of 20 hertz. Okay, what is the speed of a wave? So over here, I'm going to draw my triangle. And remember, the formula is frequency is equal to the wavelength. Now, wavelength symbol looks kind of like a weird H. And this, remember, is velocity or the speed of a wave. So on here, 4 meters, meters is a distance, and distance would be right here. So it would be 4 meters. I'm going to put M because this one, wavelength, is measured in distance. Okay? And then the frequency is 20 hertz. So 20 would go here. And then it's Hz. And then they want to know, you're trying to solve for speed, and speed is this one up top. Now remember what I said, side by side you're going to multiply, and 20 times 4 would be 80 on this one. And speed is measured in meters per second. Okay? Meters per second. All right, so let's look at problem number 2. A wave has a speed of 10 meters per second and has a length between crests, those two crests, of 0.5 meters. Now you're solving for frequency. So when I set this up, remember, frequency is down here. This is what I'm solving for right here. So I have my wavelength, which looks kind of weird, H, and then my speed or velocity of a wave up top. So on here, I know that speed travels at 10 meters per second. And down here, the distance is 0.5 meters. So when I take 10 divided by 0.5, when I plug that into the calculator, one's on top, one's on the bottom. That means I'm going to divide 10 divided by 0.5. I will get 20 as my answer. And then the down here it's in hertz. Okay. Now I'm going to pass this one with the speed of light and sound. Now we do have some wave interactions, and these are how waves behave when they go behind a barrier. And so we have 4 basic types. We have reflection, refraction, diffraction, and interference. So the first one is reflection. And think about this, when you stand in front of a mirror, these waves, they are actually going to bounce completely off. Okay? And the only one we're really going to worry about on this one is regular. And that means it's actually going to come in and bounce off at that same angle that it comes in. Another example of reflection would be sonar, like when you get into a submarine and they are trying to track things. Also with the Doppler radar, or with the Viper that you hear on TV with the weather, it's using sonar, it's using sound waves to bounce off how fast it's approaching. And also that radar detector that the cops have on detecting the speed of your car, they hold up that radar machine, radar gun, and they're pulsing out sound waves, and it'll bounce back. Okay, and as I said, regular, we're only going to worry about regular is where all waves bounce off of a surface at that same angle. If it comes in at 40 degrees, it bounces off at 40 degrees. All right, the next one's refraction, and that's where you're bending of a wave as it enters a new medium. Okay, and so as it comes in, it actually will slow it down depending on the material. If it's going through air, it's going to move faster. When it goes through water, it's going to slow it down. And when it goes through a solid, it's going to go even slower. So in there, and you can see as light comes in, it hits the water, and then it bounces back. And so the object appears out here, but it's actually in a little bit because it will travel, light passes through the water here, but then it bends and moves a lot faster there. Okay? So it's bending. Diffraction is where if waves are bounced off, and let me come in with a pen, if they're coming in right here and then they're bouncing off, whoops, we have right here, and once they hit that barrier, then they kind of will pass through and they'll kind of pulse out in a different direction, this way and this way. So diffraction is kind of bending of a wave around an obstacle. So like if you open up the door, the classroom door, you hear conversations of other classrooms around the barrier, okay, around that door. And so what's happening is sound is actually traveling down the hallway, bending around the classroom to where you can actually hear it, okay? And then interference is where you have two waves that collide together, and they can create either bigger waves or they can actually destroy the waves. Destructive. Okay? So let's look at constructive. Constructive waves are where you're taking a wave here and it's coming in at this direction. And then you have another wave and it's coming in constructive in the same direction it comes in. So when the two waves collide, they're actually going to produce an even bigger wave when they collide and hit. So it makes a much bigger wave. Okay? Destructive is where you have two waves that when they come in, they're actually going to cancel each other out. So like this one's coming in here, and when they collide, they actually cancel out, and you have a area right there, it's called a node, where it doesn't move. It kind of cancels the movement all the way. Okay? Then the last thing is our electromagnetic waves, and these are arranged by wavelength and frequency. And these waves actually can travel through a vacuum. Vacuum means no air. So it travels best in space. Okay? And the electromagnetic spectrum is also called the EM, electromagnetic spectrum. And this is also, when you look at this chart right here, moving from left to right, their wavelength decreases. You can see we've got less waves to more waves. Remember, the more waves you have, the smaller or the lower the wavelength. but your frequency increases because we're getting faster. So in essence, when you look at this, they're moving from slower to faster waves. Slower to faster waves on there, okay? So radio waves, if I go back to this chart, radio waves are the first ones. We're actually going to start with the slow waves and work our way to the fastest waves. So radio waves are your longest wavelength. They have the lowest frequency, and examples of radio waves would be TV, microwaves, radar that's out there, even radio waves, radio transmissions, radio towers. All of those are examples of radio waves. Infrared is what they use for like CSI, when you see military going in, they're wearing the goggles, the night vision goggles. They can't see a person, but they see the outline with heat given off. They're used to detect heat. Visible light is what we see. When you look around all the different colors, light, when it enters our Earth's atmosphere, is actually white light. But once it hits the atmosphere, when it hits particles, air particles, clouds, anything that clouds it starts to slow it down. Remember that bending, refraction. Light will bend, and it bends in the color of the rainbows. And it's also called Roy G. Biv, standing for red, orange, yellow, green, blue, indigo, and violet. Indigo is kind of like a blue color. And then violet. Violet being the fastest. Red is the slowest color. Violet down here is the faster color. Okay? So red has the lowest frequency. Believe it or not, red is the slowest color, and your violet is the fastest. So it has a short wavelength, high frequency. Then we have our UV, or ultraviolet light, or rays. This is where, if you go outside, it's good for your body because it produces vitamin D. But unfortunately, if you're out there too much, you can get sunburns, which can lead to skin cancer, melanomas. Unfortunately, we can't see the UV rays that are out there. UV ray, I believe A and B, and now there's a C. X-rays are ones that were where you're used to take x-ray of bones. It'll pass through your tissues, organs, things like that. It actually can pass through it. It's kind of mushy and soft, but when it hits the bones, it bounces back, and that's why we're able to actually see your bones in your teeth and all the skeletal bones there. And gamma rays are your fastest ones that are out there. They're usually, most of them are found in space, but they also use it with gamma radiation to kill cancer cells in the body. In order to stop it, though, you can stop it. Lead can stop it, but you got to have 3 meters of concrete or lead there. Actually, the lead doesn't have to be 3 meters. So let me correct this one. It's 3 meters of concrete, and put the concrete there, or just a thin layer of lead. So let me write the concrete. E-T-E. So concrete is C-O-N-C-R-E-T-E. Concrete, or just a thin layer of lead. Okay? Hope this helps you. And